Okay. So we have dealing with space, function space. And use a better notation if you want, but use this notation. Since we put a 0 here, that means infinity. So we use this notation. Functions C pi. And this function is 0 to pi. Sides the value at the end points coincides. F of 0 equal to f of 2 pi. We identify this C0. Identify this with functions on circle S1, which is all those z such that mod z equal to 1. We can also identify this with our periodic functions on R with period pi, with period 2 pi. Okay. If you want, we can identify this. This we identify with this. Okay. Or we can identify with minus pi also. It is just translation. F going to F F pi. We can identify. We can define an isomorphism here to here. See, if we have two algebra with a norm, this is not just algebra, this has a norm also. Normed algebra. Algebra means it's a vector space and it's also a ring multiply. Okay. And if you have a, so then something is you identify two algebra with two normed algebra, which has a norm, which has norm linear space, like norm linear space, we can talk about normed algebra. So if we have two normed algebra, if there is an isomorphism between them, by that we mean there is a bijection, which is also a homomorphism, which is also a linear map, and it preserves the norm. It preserves the norm. The norm is same. Okay. So then we can identify there is no difference between them. So they define from here to here, you can define a new function f prime at t equal to f of you want to have phi or something. Okay, phi will values here, right? So you can define that and you can identify any two function. And this is you can see that it's supremum. If you calculate supremum and other things, it's non-preserving. It's homomorphism. The multiplication is just pointwise multiplication, it will be a homomorphism. If you apply the definition of homomorphism, linear map, everything will be satisfied. So this is we prefer to work with this. Okay, this is what usually we want to work, but for something we may work with this. Sometimes it's better to, it's easier to work with this. Okay, since it's an isomorphism, whatever you do here, you also. Okay, but it's easier to work here. So yeah, something like that. If you something minus delta to delta, exactly, can do things like that. Okay, that's why it's easier. Okay, so yeah, we have the following proposition. Then you define L2 equal to closure of. Also doesn't matter. It is just the closure norm. Okay, where norm 2 or inner product. Okay, inner product. Inner product gives the norm, and it is that norm we take. But it's better to define inner product. Okay, fg bar 0 to 2 pi. Yeah, 1 by 2 pi fg bar. F of t, g of t bar. Okay, these are all complex valued functions, and you integrate with respect to. Yeah, it's a completion. But I forgot to put a bar. Yeah. Okay, it's a completion with respect to this inner product. It's what we call as L2. Then I think I gave it an, but I gave the argument. Then we have remark or whatever. We define P n at t to e power int, okay, which is a function. Then P n t n in z is an orthogonal basis for L2. Okay, it is an ortho. Yeah, proved it. Didn't I give it as an assignment? Okay, gave. Okay. Oh, inner product is continuous. Okay, okay. So anyway, the argument is you take by Stone-Weierstrass theorem, these functions are dense here, for example, dense here. I mean, which is a z power n, where n ranges between n is in the integers. So which is dense here. So because of that, because C0, this is a, I mean, we defined that C of x where x is a compact or something. Here we are considering C0, there may be a confusion. So better you apply to this rather than that. Okay. So all functions z power n in z. Okay. You take this is if you take the linear combination of this, that is a algebra. It is just polynomial, or if you take a combination of those functions, that is an algebra. Because e power int, e power imt will be e power n plus mt, so it will be again of that form. So linear combination of these kind of functions is an algebra. That algebra is dense here in the uniform topology, in the norm topology. But then something is dense, something converges uniformly means it converges in L2. So it is also dense here in L2 topology, L2 norm. But then if you take this is dense here, but this is dense there, but this will be dense there. Okay, that is an argument we know, we have seen earlier. Okay, so because of that, this is not, I mean, dense means not, this is not dense. Linear combination of these things are dense there. That is what exactly the definition of orthonormal basis is. Okay, so this means, but then orthonormal basis, I mean, orthonormal basis, the definition is if you, it is just if you take the linear, first of all, it should be orthonormal, that you can just take the inner product between phi n and phi m, that will be delta nm. That is clear. You just compute the inner product only when n equal to m, it's going to be 1, and it's because you are dividing by 1 by 2 pi, that will be equal to 1. Otherwise, it's 0. If you integrate for int between 0 to 2 pi, because the end point is same, it will be 0. Okay. So so it's an orthonormal basis. And so linear combination of that is dense here. Okay. And but this is an orthonormal basis. We have some 4 equivalent conditions for orthonormal basis. One of them is this condition that linear span is everything. It's an orthonormal and linear span, it generates the space. Linear combination is everything. It satisfies other condition also. The other condition is if you have any f in L2 0, then f is equal to summation function. As a function, I'm writing. Okay, n in Z. We proved for n in n, but you can, I mean, since the same countability, you can take it to be n in Z. Okay, this is true. So what does this mean? This equality is in the space of remember. Okay, this is the what? L2 here it is separable because we already got a countable basis, so it is separable. Closer? Say it again. Closer. See with this. Yeah. I mean, in L2, it will be okay. It will be finally be everything will be same. L2 2 points are equal, have any meaning because it's up to equivalence class only. The endpoints are, you can change that to something else if you want. Okay? That will be the same function because L2 is, I mean, actual L2 is actually class of function. Anyway, it doesn't matter for you. We are just taking the closure. You just take this definition. We're just taking the completion, not closure, the completion of this. That's what we are calling L2. Okay? C02 pi, yes. C002 pi. What do you mean by C00? Means the endpoint coincides. It will be, see, you have a circle. It is just C0225 L2. Okay. And I mean, it is just one point. It is just same as that. Okay. Anyway, let's take this definition, doesn't matter. That is just an example I gave later. So let's take this as the definition, okay? For us, this is the definition. L2 is just the completion of that. Okay? Then any f can be written like this. What it means is take any f. So in particular, if you take, I mean, suppose if so in particular for any f in any continuous function in C02. So f is equal to so what it means. Okay? I mean, I'm writing this. Just means okay? Correct. So SNF you define as T. Yeah. F P which is equal to summation n equal to n. Okay? F P n, you consider this. So which is just so and you define equal to P n which is equal to 1 by F E F hat n. Okay. So having F hat n e power int. Okay. This is our Sn as functions. Okay, for each t, it is the case. Then this says that whatever the orthonormal says that Sn f converges to okay, that's what this says. This says that SNF, which is just a summation. I mean, as mod n goes to it should go to infinity both sides as mod n goes to infinity. Okay? So that is what here there is no modern. Here because we are taking sum from minus n to n. So yeah, for this is enough. Okay? So what does this mean? This means limit n going to infinity. Integral 0. Mod of square dt this goes to 0 equal to 0. Okay, this is precisely the meaning. So we started a function. We defined something called f hat. F hat is a function from okay. F hat is a function. We got something called Fourier coefficient, which is a function on n. So we had a initially function on 0 to pi, or a periodic function on real line, or a function on a circle. Then we got a function not n z. We had a function, discrete function. We had a continuous function. Using that, we got a discrete function. Then using the discrete function, we can get back this function, but in L2 in that sense. Okay, that's what this says. Okay, so this is what this Fourier analysis is about. You define a function on some group, then you define corresponding Fourier transform of that on a different space, which is usually called dual of that. Okay, it is called dual. The Z is the dual of 0 to pi. A real line is the dual of real line, or if you take a circle, this is a dual of circle. Circle is a group. Okay, or you are just identifying that with the group. So if it is circle is a group. Okay, so the dual of that is dual. Huh? Yeah, I mean, yeah, we don't whatever. So this is called Fourier series, but on real line it's called Fourier transform. Generally, this study is what is called harmonic analysis. Okay, so you have a generally you take a group and you take the dual group, and by analyzing I mean, what is the relation between the f and f hat? Okay? That's what this is a whole big subject on its own. And this has applications everywhere, differential equation, this, that, everywhere. It's just application, technology also. All your digital, all those things are uses this. Okay, I mean the digital is some sort of Fourier transform, and you get something discrete, and yeah. So it is just continuous function. You want to study a continuous function, you study a discrete function, and then using its property, you will get back the property of that. So that is the idea. So, so what we have is following here. So we have got, but do we have point-wise convergence? So this is the question. Yes. For f in any function, so we usually consider this kind of function. Okay, we got this L2 that based from the basic Hilbert space theory. Okay, C0 2 pi SNF at P converges to f of t. Okay, that's the question. Or whatever. It only matters the okay, this is the question. Okay, but that this does not happen. Okay, so that's what we will do in this class. Point-wise convergence. You have L2 convergence. That does not mean point-wise convergence. So point-wise convergence does not happen even for continuous function. Before that, take some remark. Okay. First one. F F function are in D0 2 pi. F at n equal to functions. Okay. For then f equal to g. F of t, f equal to g. I mean, as far as they are same. Okay. Reason, I mean, this is just you see this map. You can define how do you call it? I'm using it for another thing. Say this map L2 from 0 to pi, okay, to this small L2 of z. This is discrete, so I'm using small L2. Okay, we define a function where this function f f is a function on that, f is a function on that. Okay, this preserves the norm. This is an isomorphism. I mean, isometrical isomorphism. Is product. Okay, I will tell you the proof and leave this as an assignment. Okay, this is very easy. What is an isomorphism? Be a bijection, number one. Okay, it should be a bijection, and it should preserve the inner product. It will preserve the norm when for a norm linear space. For this, it will preserve the inner product. It will be inner product between fg bar. It's just to understand that there is really nothing. Okay, that's the inner product. G product there. It follows. Actually, there is really nothing. It is just. It will take 10 minutes. It is just for you to understand. Product of fg. You know, by n in z. Okay. In L2 inner product. Okay. So this is of Pn. This is the property of the orthonormal basis we approved. Yeah. Does it look something else? Yeah. This is the property of orthonormal basis we approved. Okay. This is just an in the height. And then maybe the bar. G. Huh? So I read, no, why I changed it. Okay. That is exactly the inner product. It's not an assignment. It's clear. Okay. Where norm of So this proves that similarly, if you have anything, then that defines. So you go through the property of the inner product. Similarly, if you have anything here, there is a last proposition. If you just use that, you will get that. You can define a function here. So it's on to also. This one, if it is 1, 1, 2, this is just says it's 1, 1. This is 1, 1 onto. That's why I asked you to verify that. Okay. You want it's not clear to you? Okay, then it's an assignment. Okay, just write it. Sorry. It is just an assignment. Just you see, prove this. From this, it of course follows. I mean, it's just part of this, right? So make sure that this is an assignment. I thought I already given you the proof, but since it's not clear to you, you write it as an assignment. Okay. Similarly, this is also true. Norm 2 is same as summation square. Okay. The L2 norm in the L2. That's what this says. Okay. So from the things that follows, it follows. Exactly. That's what in particular I said. Yeah. This is to prove that. I don't know whether you have seen. For giving example to that, do you know this value n equal to 1 to infinity 1 by n square? What is the value of this? Do you know proof of it? You don't know proof of it. How do you know it's pi square by 6? You told pi square by 6, no? Let us see whether it's correct. If you haven't seen the proof of it, let's prove it now. Huh? Lights, ah? What? Yeah, there is a video. Whose video? YouTube channel. So there in internet, there will be there. Then you don't need to. So everything will be in internet somewhere, or in books somewhere. It's there. Yeah, yeah. We here this using this using this will prove. Okay. Before that, we need something else. Now this proposition. Okay. C is R and the same. It is just real part, imaginary part. Is that Riemann integral. Okay. Then direct this. You can change the value. You can change the value. No, you don't. It's not true. I am a function that is not true. So yeah, you can. Be 0 doesn't matter. Okay? It's still very manageable function. Yes. Not manageable function, but the endpoint value is different. But you can change it to f of 0 equal to f of, you can take it to be f of 0. Okay, that's the same function. Then C0, right? Then given epsilon, then for given f such that this is G. Okay, E the continuous function. You can estimate Riemann integrable function, bounded Riemann integrable function, because any continuous function on this will be bounded by a continuous function for any given epsilon. This is clear to you? Exercise. You take upper sum, lower sum. They are just basically step function, right? You take the minimum. If you take the minimum in an interval, so this implies given epsilon greater than 0, the partition. Okay. Partition is number. So 0, 0 equal to t0 less than 1 up to tn, which is equal to 2 pi. There exists a partition. The upper sum, lower sum, right? So lower sum, that's what it means by Riemann integrable. Or of f of t in okay. You can take it if you want. Same. Okay. Then this capital Mi minus mi plus 1 ti. This is the, okay. So if you define a function, if you take the value in this ti plus 1 mi, capital Mi, okay, is the difference between the integral of that function and integral of this function. Okay. Now you just have to find a function which is, which is between these two things. You can find a continuous function. Okay. Shall I leave it as an exercise? Okay. Huh?
For this, if we just we define this inner product on C0,
yeah.
Instead of that, can we define norm as integral? Instead of mod f square we are getting, can we write it as mod f?
Integral, say it again. Instead of
norm we get from inner product is mod f squared.
Correct.
Instead of that, if we get mod f, would that still be a norm?
I don't understand what you are asking. This is the inner product.
Instead of defining inner product, if we just directly try to define a norm.
Yeah, that's okay.
So that
same thing.
We get something else where that is the method. Then we will be done directly.
It will be done what? Oh, you are exactly done, but you have to prove that the Riemann integral function is in L2. No, here by our definition, that is why we are using. Okay, well, I understand your question now. So that's saying all L2 functions, which is already proved. You are saying, but for us, we defined it to be just the completion, topological metric completion. We haven't defined what is L2 function and other thing. No, so you are right. So I am just saying that a Riemann integrable function is an L2. That's what I am saying. Okay, here it is actually L1 norm. But then if you have a L2 norm, you can take it and minus that will be bounded, you can take it out. So that if you have a square also, this is okay. So I am exactly. I am stating this because the Riemann integrable function is in L2. Okay, because we haven't defined L2 through functions. We have defined through metric completion. Okay, I'm just saying that any Riemann integrable function can be approximated. So you can consider a Riemann integrable function. You can still define, and again, why L1? Of course, you can define L1 also by if you close with respect to L1 norm, which we have defined already, then that will be L1 of that. Okay, so L2 will be contained in L1 in this case for bounded intervals. Okay? So that is why I use L1. You can use square also. Okay? So the reason I want to prove, he asked the right question. The reason I stated that lemma is, which is actually clear, is I want to say any Riemann integral function is in that L2. Because I want to apply to a Riemann integrable function, not to a continuous function. Okay. Let f from 0 to pi to c are defined such that f t equal to 1 if t is in 0, maybe this, okay, equal to 1 if t is in pi 2 pi. Okay. And if you want, okay, pick pi the endpoint, if you want to coincide on the endpoint, if you have a problem with that, f of 2 pi, define it like that. It doesn't matter. What value takes at 2 pi doesn't matter. Only this interval empty. Okay, this is a Riemann integrable function. Okay. So I erase, I erase. Oh, supposed to go to that board. Okay. So we take this function. Then it is because it is approximated by continuous functions. You take a Riemann integrable function, then this clear because you can approximate with the continuous function. Okay. Hmm? Yeah, it's a completion. So there exists. So f is in L2 0 to pi. Simple f2 square equal to n square. Right? This follows from that. So I just apply this to compute that series. Okay. Take this function, which takes the value of 1 between 0 to pi and -1 between pi to, which is a very simple function. Okay, which is actually called a simple function. Actually, this is what is called a simple function. So very simple function, and it is Riemann integrable. So it is approximated, and it's approximated by a continuous function. So it is in the L2, whatever, however we defined as L2. If you go through the general definition of L2, it's clearly there. But if use our definition of L2, so then also it is there. So this follows because from whatever we have proved, this is true. Okay, let us just compute. Norm f2 square is just 1 equal to integral mod f square by 2 pi. Okay, right? It is just 1 because it is -1 and 1. It is just 1. Okay. So we don't have to calculate this. Okay. Function n in z f hat n square. This is what you want to calculate. It's the same as n z. Take the square of this 1 by. So let's calculate this and then insert this. Okay. We want to calculate this. Erase this, the whole thing. So we have to calculate your coefficient equal to 1 by 0. Okay. Here it is 1, here it is -1. So I put 1 only. I mean, I put a minus sign here. And what is the, so we have nothing, only we have the phi and t only here. Phi and t is cos, just phi and t e power minus I n t, which is cos of that and sine of that. Cos of that is cos, I mean, if you take, I mean, if you take the cos of that, whatever, that will vanish. Cos will become sine if you integrate it, and sine of pi and sine of 0, 0, this also 0, 0. Only cos matters there. So only the sign matters there. Sign matters there. I mean, the integral will be cos. Okay, but then you have minus sign, e power minus int, so you have minus sign. Okay, but minus of sign, the integral of sign is minus cos, right? So the minus will go away. Okay, so I just know that. So I'm just 0 to pi. We get, so what will you get? Minus of that, which will be cos cos int, no, int, cos I, not again, cos nt divided by n, okay, between 0 to pi. But here you will get the minus of that, right? Here you will, I mean, here it is at 0, cos is 1, here it is minus 1, but here is minus 1, it is 0. Okay, so it will be 2 times that. I did 2 times that. I don't compute. There is an idea. Okay, when we take the square, it, okay, and here there is there a minus here? Here minus 0. This is minus. So minus I times 1 by pi, okay, into cos pi. I mean, okay, this is only for f is 0. Sorry, f hat 2n is 0. F hat 2n is 0. Because when it is 2n pi, it's 0. Okay, only for f hat 2. So 2 will cancel, which will be minus I. Do this computation. Okay, minus I cos of 2 divided 2n plus 1, which will be minus 1. Yeah, there is a pi. You tell me whether you find it wrong. If there is something wrong, we won't get the right result. Okay. Is I am to put 2, no? Correct? 2, no? By 2. Correct. Yeah. Correct. I think this is correct. Okay. But then f of 2n plus 1 is same as f of minus 2n plus 1. Okay. So this can square. This is what we are computing, n in z. If we take the I mean minus I square is 1. Okay. Because we get 4 pi square 2n plus 1 square. Okay. There is another, there is two things. Negative sign. Absolutely. Go away. 8, right? I'm supposed to get 8. Why am I getting 4? There is a 2 missing. No, there is already. I'm taking a square. Sorry, I'm taking a square. This will become 4. And then there are 2. F at and f at minus and square, both are same. Yeah. So there is square is 4. So 2 into 4. So I'm getting this. Sum will be 0 to infinity. It will be 0 to infinity. You are right. N equal to. You are right. 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 N in Z. This is right. And here I haven't written the sum here. Here it will be n equal to 0 to infinity. 1. Yeah, 8. Or if you write it as 2 into 4 pi square. Correct? 2n plus 1 square. Okay. Okay. So the 2 is coming because minus n and n mod by are same. Because of this 4 is squaring that. Okay. And I square minus I square is 1. Because of that, and 2n square is there. Okay. If you do the I mean, it's better to do the computation. So these things implies 1 by 2n plus 1 whole square, n equal to 0 to infinity, equal to Okay, this is what we have got. But then summation, I mean, if S is equal to summation 1 by n square, n equal to 1 to infinity, then S is 1 by 2 n square you can calculate, which is just 1 into S, right? So this implies 3 by 4 S equal to, this is what we have got, T. So S is equal to 4 by 3 into 8. Okay, that's what you want. Got the answer. Okay, pi square basics. We just, I mean, these are just elementary computation, but we use the crucial thing that this Fourier L2 norms or Fourier transform is an isometry. That's what we use. Okay? If summation f hat square is same as the inner product between, I mean, norm f square. The main it's here, right? It's this. This is what we use. We computed this norm. This is 1. Then we just computed this, which happened to be that. Yeah. S is equal to, then S is equal to T plus 1 by 4S. T is this. Call this as T. I said T, I didn't write somewhere. Okay, T equal to this. Okay. So S is equal to this. Yeah. 1 by 2 n square is 1 by 4 times summation n square because of that. Okay. Fine, clear? Okay. So I will give something else as assignment. You have to find the right function and compute that. Okay. Huh? I will give you an assignment. Hopefully, right. You have to find the right function and compute the summation. This is one such example. Euler's formula. So this is one such function. Okay. Like this, which is a very simple function. Like that, you have to find the right function, correct function. Okay. Yes. Or something more. Okay. I want to do for L1 theory, but let me not do that. Straight away, I will do that. The point, I will give a counter example, not counter example. I will show you that the point-wise convergence is not true. So that's what we will do now. Okay. 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 Yes. Yes. Okay. And we take continuous function, and even for continuous function. Incidentally, I said this thing I erased it. If you have that equal, then f equal to g holds continuous function. F cat equal to g hat means f equal to g in L2 as functions. But when it is continuous function, if the integral, I mean, if the integral difference is same, then function has to be same pointwise, right? We have seen it, right? So that's why it's true. Okay, so Fourier in injective transform. Okay? I mean, it's 1-1. Okay, whether this is the question. Okay, counter example. Prove this is not counter example. Okay, we will use uniform ordinal principle as promised. Huh? Yes. Yeah, it's an isometry. You can consider you have a function in L2, capital L2. So getting function is small discrete function. From this function to this function is what is called Fourier transform. Here, in general, you can take it from R to R. You can do it higher theory. Okay. Here, this is what it is. So let us compute what is Sn. So claim is a form. Let's write it as a proposition. S f at t is equal to integral 0 to 2 pi, 1 by 2 pi. In case I miss this 1 by 2 pi, it's always there. I mean, when I write, I may miss this, but you should know that it is there. Okay. We define a new function. This is called Dirichlet kernel. Dn s minus t f of s t minus s, I think. S minus t f of s. Okay. I think it's correct. This is usually solution for that. We'll have that later. Okay. So this is the where dn of s whatever is equal to sine n plus half t equal to 0. For t equal to, it doesn't matter. We are integrating, so it doesn't matter. But in case you want, I think it is 2n plus 1. Where shall I write? Okay, I'll write it here. T 0. At 0, it is 2n plus 1. It doesn't matter. If you compute the limit, I mean, this is continuous function. So if you compute the limit, it should be this. But it's only integration. We are doing integration. Point doesn't. So this is what is. I think usually kernel in algebra is something that the zeros of a function are homomorphism or something. Zeros of a homomorphism or something. Here kernel means if you have any function, you integrate it with respect to some function, you get a new function, right? You get a function at t, you are integrating with respect to s, but t is not a variable here. Okay, but t is a variable for this. So you get a new function. By integrating with respect to function, you get a new function. And that particular function is what is called a kernel. Okay, this is whatever. Yeah, right? E power I is phi and e power I n t equal to by 2 pi integral. I mean, this is just a finite sum. Take the sum inside. Maybe you write it to minus n to n 1 by 2 pi f of e power minus n t f of s e power minus ins the ds e power t minus s you will get, okay, which is equal to minus n to n by 2 pi. You can take the sum inside integral something minus n to n, okay, and this function. I mean, this is you can if you have something. Yeah. Okay. This is so you should have asked this question: what is s minus t? When you take s minus t, it is you can take this s minus t and the circle if you want, or if it goes outside that. This is, I mean, you should consider f as a periodic function. Yeah, exactly. I mean, s minus t may go outside the interval 0 to 2 pi. Okay, then you should understand that f of t is same as f of t plus 2 pi. You have to use this. Okay, you should use that too. This is same as 0 to 2 pi f of s g of s minus t dt. Just change that variable. Okay, that variable. Okay. Because that equal to theta. dx. So this is equal to, so 2 pi will be, what is? No, no, this is a general statement I'm making. If you change of variable, general statement, going to apply generally. There's no t here. Because of that, this is equal to integral 1 by 2 pi integral of minus t f of x, where dn may you use some other variable if you want. If you have any group, you can shift one of them. Just the translation by integral f of s plus t plus integral f of s, right? T is fixed. Whole thing. Okay. The group. If you want, you take the whole thing into circle, it will be clear. Okay. Convince yourself. Okay. You have explained the thing. Yes. Plus. No, no, no. It will be like this. There is no plus. Yeah. No, it should be, cannot be plus. This is logical conclusion. It will be like. This is just says that the so-called convolution property is commutative. That is convolution product. You get a new function in T, no? That is convolution. If you have time, you will do that. Okay. Where D and T, yes, you forgot this. Here we have got tan of is just this, which is equal to this. I take the summation inside. Okay. The dn function. Okay. But then if you have f of s, so I use this to say that f of t minus s here, s minus t here, and dn of s here. Okay. I have interchanged f and t using the change of variable formula. Exactly. So I got this. So where d and t is this, all I have to calculate is this. Zero to 2 pi is also a group. You identify with when we have that periodicity, 0 to 2 pi is also same as that. You are identifying with the circle, anything. If you have confusion, go to the circle and come back. Circle is a group. Like 0 to 2. See, how often mean by 0, 1? What is Z3? 0, 1, 2. What do you mean by it's a group? If it goes, you will subtract it. Similarly, exactly that. 0 to, if it goes beyond that, beyond 2 pi, minus 2 pi, I mean, get that. Okay. And yes. This should be t minus s. Yeah, here also it is t minus s. Right? But you, but you are, I was objecting to you saying one place it is minus, one place it is plus. That is what is, both the places it's fine. This is fine. T minus s. Yeah, sorry. I'm sorry. Yeah, this is, huh? No, It is t minus s both the places. Now what is the problem? Now you here have e power minus in t minus. T minus s. Here also it is t minus s. Everywhere it is t minus s. Okay, I'm sorry for this. Okay. This is okay. Okay. It's a very in confusion. So DNT is this. DNT is this. We have just compute this, which is just a geometric series. First term is minus INT. First term is this, and then this R is E plus term. E power, sorry, I write it like this: E power I 2n plus 1 t. Okay, minus 1 divided by t minus 1. Right? This is correct. So now this is equal to e power int. If you take it, e power, if you have n plus 1 t, n plus 1 t, I n t plus e power I t minus 1. Okay. Formula. T by 2. E power minus n minus t. E power I t by take it by 2 minus e power. Same thing. I have just put e power I t by 2 every both the places and cancel. Maybe I in n plus half t by sin t by 2. Okay. This is what we wanted. Sin 2 n plus half. This is what I like. This is the formula. Okay. So S is f of s, then dn is this. Okay. So we get this. Okay. So we got this. Good. So if you take this, get, I mean, don't need formula. If you integrate dn, okay, we don't need it. I'm just remarking in case we need it. Okay. We'll get to that later. Okay. Going to infinity, 0 to 2 pi, by 2 pi. It diverges. Okay, this is the claim. Our DNT is this. We want to use this formula. Okay, proof. Like a DNT dt equal to, which is just 2n plus 1 by 2, right? 2n plus okay dt, okay, mod. Yeah, it's very important. If there is no mod, it is just 2n plus 1. That also goes to infinity. To 0 to 2 pi. Okay. Now greater than or equal to sin t by 2. Sin t is greater than or equal to t. when t is greater than 0, right? That's clear? Yeah, sorry. T minus sin t is greater than 0. T minus sin t is greater than or equal to 0. Okay. So if at t 0, it is 0. If you differentiate it, you get 1. Okay, which is greater than or equal to 0. If it is positive, at 0, it's 0. So it's in because of you can replace this by put a greater than say equal to, I put a t by 2. Okay. So 0 to pi by t by t. Yeah, the t by 2 I have put. Ah, okay. Anyway, it doesn't matter. We are going to take to infinity. Okay. Substitute. This is equal to integral 0 to so I mean that is one thing. I don't know whether we need it, but we can instead of 2 pi, we can take it to be anything near 0. Okay. I mean, actually only need pi. I can take it to be delta, which is something less than this. Okay. I mean, this is just you can use 2 pi itself, but for even for delta, this will be true. Okay. So if you take delta, okay, any delta, as far as delta is positive. Okay. So 2n by 2. Okay. And ds and this there is a dt and there is a, I mean, when you change to ds, those constant will go away. Ds by and there will be, is there anything more? Okay, is there anything else? It's okay, no? That's all. Huh? Mod. Also, there is a mod, sin s by s. So this is what we have. Okay. Now we say that this is greater than or equal to some n corresponding to that. This is greater than or equal to, because it's easier to write like that. 0 to n pi, some constant k. There is a delta. What is that? This ds and s, that the constant will, there will be a constant. That constant you will get ds and s. It will cancel. Okay. Whatever the constant is. So n goes to infinity, you will have a n which will also go to infinity. Okay. As infinity, n also goes to infinity. N. This will go to infinity. Okay. So corresponding to this n, we will get some n. So that I can write it as n pi. Okay. So some there is a constant, I call it k. Okay, whatever. So mass by s ds. Okay. Now this is greater than or equal to some k times. This is s is 1 by s. This is I mean, so you can write it as summation. I wrote it like that because I want to write it as summation. Summation k equal to 1 to n integral 0 k minus 1 pi to k plus 1 pi k pi mod sin s by s ds. Okay. For k equal to 1 to k pi. I can write it like that. And 1 by s, I can replace it by k. Where is k is already used? K is capital K. That's small k. You want m? Okay. Are you okay? That is capital K. This is small k, small letter. What is that? K minus 1 pi to k pi. So t n pi. I wrote it because I want to write it like this. You have 2n plus 1 delta and other things, but you can get a n pi so that when n, this n goes to this n goes to that, right? Some n. You can take it n smaller, n pi smaller than that. Okay. So then I write it as k equal to 1 to n, where k minus 1 pi to k pi. This is clear. This is k minus integral k, maybe earlier one was better, to k pi. Okay. Okay. Is okay? You can see. Okay. Okay. Lara, haven't changed it. Hopefully, one can see. I will show this. You can see this. Okay. It's all the computation is there. It's very simple. Very simple. Now you have to freeze it, and one window you can freeze it, the other window you can hear it. Okay. In case you want to go through, it is very easy. You don't have to. Okay. Now that is so in some m summation k it already 1 by k integral k minus 1 pi d for all k, right? 0 to k minus mod sinus is same as k minus 1 pi to k pi. If you take between 0 to 2 pi, that is 0. But when you take the mod, this is from here to here, it is same number. So this whole thing is greater than or equal to some times summation k equal to 1 to n 1 by k, which goes to infinity as n goes to infinity. Also as n goes to infinity. Yeah? That's all. I take here it is this 1 by s. I have replaced it by 1 by k pi. 1 by k. 1 by k pi or the k that's taken inside is a constant. Okay. This follows everything. Yeah. If you want, otherwise okay. Follows all the constants. As far as the constant does not depend on n. Okay. This goes to infinity. That's all it is. Okay. Now let us define. Now let's prove it. Define Sn n from C0 to pi. It's a backspace with respect to norm infinity. Okay. Yes, counter example. Yeah. So far, I'm giving a counter example. Okay. Uniform boundedness principle as promised. Okay. Exactly what I proved. I will show you and something which is an exercise. I don't want to give it as an assignment, but if you go through the proof, you will get convinced. I should have proved this rather than that, but both are same. The proof is same. I will tell you how. Here to C. So Tn is a map from C0 to pi. I mean, to specify the norm I have written. Okay, it's a map from. This is a. Did I say Banach space? This is a complete norm linear space. Okay, that's what a Banach space is. Okay, you might be knowing. So this is a map from this vector space to C, which is I want to define a linear map, and the norm is here. This. Okay, which is just Tn at F. Okay. So Tn at F, that's what I have to, we have to get a number. It's C. So which is just Sn at F. Which is a number. And it is linear. Okay. If you take Sn, that is Sn is defined like this. If you have a lambda here, you can take it out. If you have this is integral, you can write it as Fn plus F. This is what Sn is. Right? You can see that it's linear. Okay. T is linear. We have to prove about that. Linear. That is clear. Okay. Because of that formula. Dirichlet, it's a integration with respect to Dirichlet kernel. Okay. Whatever we call it as integration with respect to that, and it is linear. Okay. This is the problem. We want to yes. So to prove continuity, we have to prove it is bounded. Whatever we call it as bounded linear operator. We have to, I mean, provide norm is not infinity. We have to prove the norm is bounded. This is equal to 1 by 2 pi 0 to 2 pi mod dn dt. Okay, this is the okay. So how do you compute mod? How do you compute norm of a linear operator? Okay, if you have, this is just explaining, I will erase it. Okay, we have some non-linear space to some other non-linear space y, whatever, or is better you have take it as C. For here that is the case. You want to compute, okay? What will you do? First, you have to consider the Cx from or norm x equal to norm x equal to 1 or less, doesn't matter. Okay, less than or this is the norm, right? You take the supremum of this. So to prove that if you take any element norm x is this, or it is also the case that it is the supremum of all those things, k minimum of all those k satisfying something. That's also we proved. But anyway, it is that. So first if we prove that if is less than or equal to is less than some m, then the norm is less than that. Then you have to prove norm is attained. Norm is attained, you can take some element and prove that that number is attained, number one, or you can take a sequence of things which satisfy this, which converge to that number. That's also fine. Okay, so so f is in Cn, C0. Okay, then mod of this is a function, so mod of Tn f to mod of Sn is equal to at 0, when t equal to 0, we have to compute this. Okay, this is a even function. Okay, I mean both the places, if you take minus minus, that will cancel. Okay, so this is just equal to integral 0 to dn dx. You just Sn f of 0, you just substitute 0 in this formula. Okay? If you just substitute it, you get Tn of 0 is this. Okay, there is no mod, it is this dns 0 to 2 pi. That's what we get. This is what is this mod. Here there is a mod. Okay, and which is are equal to 1 by 2 pi integral 0 to 2 pi mod dn x ds. Okay, this is less than or equal to this. So this implies what? F of 0, Sn f, Sn f 0, Sn f 0. Sorry, SNF is another. Okay. SNF is another function. F is a function, SNF is another function. It value at 0 is what I have written.
times fs.
Fs ds. Ah, sorry, correct. So sorry. SNF at 0. That's what I said, but I forgot to write it. Yeah, 0 to dn of good dn of minus s, which I take it as s. Okay, then f of s ds mod s. No, dn of s is same as dn of minus s. I'm not, if you wish to write it as. Okay, you write it later, change it. Okay, this is mod. I'm sorry, this is less than or equal to 1 by 2 pi. I'm sorry, it was a mistake. You pointed out. Okay, which is equal to, this is f. I mean, here, this is less than or equal to, I take the mod inside. Okay, mod inside. And this mod f of s, you can take the supremum of f in outside. Okay, so this is less than or equal to norm f infinity integral mod dn s ds. Yes, sorry, there is no t anywhere. Ds. Okay, why there is a ds and I wrote dt. Okay, okay. So mod of tnf, okay, is less than or equal to There is 1 by 2 pi already written here. Okay. Yeah. From there, if you take, I want to compute the norm of this. Okay, this is a linear function from this. Okay, so I'm computing mod of which is equal to this, which is just substitute 0 in that the formula. So you get this. Okay. This is less than or equal to, I take f of norm f infinity outside. We have done this in probability and everywhere. So norm f infinity outside. So norm f infinity times this number. Okay. So we have this. Oh, I have changed it here. Sorry. You have to show this. Why? To prove it. What is the question? To prove whatever we want. Huh? Huh? That is over. We have proved some inequality for L2, and we gave an example for oil of where it is useful. Now L2 theory is over. We are not going to talk about L2 theory. Now we are considering whether there is a point-wise convergence. Okay, so we are using now. I am defining here. You should have asked here why I am taking norm infinity here. I am taking norm infinity here because I am considering this is a new theory. That is L2 theory, which is over. I mean, there everything converges. It's nice. Okay, here it's not nice. That's what I'm showing. Okay, so to start with, we defined Tn to be this. Okay, then I want to prove this. To prove this, I have to compute this. Okay, so I compute Tnf, which is equal by definition. If you insert 0 in that formula, we get this. Then it is just equal to norm infinity times this. Okay, so these things prove the following. Which one I should erase that? Have to erase this. So this thing applies less than or equal to R dt mod of times norm of, right? That's what I approve. Norm of Tn is less than this number. By definition, for example, if you take f infinity less than 1, then Tnf is less than 1. This norm is just the supremum of this Tnf, where norm f infinity less than or equal to 1. Okay, because of that, this is true. Now we have to prove that the supremum is attained here. For that, what we have to do? We are, see, our Tnf is this, right? Tnf is this Tnf is equal to, okay, Tnf ds. Okay, so if we get mod here, that's enough. So we can actually use function for Tns, but we can't use it because this will become 0 in many places. The sine 2n plus 1, that is becomes 0. So because of that, okay, for epsilon greater than 0, or 1 by n, you can take epsilon, or you can take 1 by n, epsilon 0. Let f epsilon is equal to 1 by square of square plus epsilon square. You wish epsilon or epsilon square, doesn't matter. Okay, this function will not vanish. Okay, but as epsilon going to 0 and no is less than or equal to 1, no, not epsilon. So Tn by square, I mean there, Tn square, this less than or equal to 1. 1 is an integrable function. Okay, taken too much time. Are you tired? But I have to do this. I'm sorry. Euler's formula. This is less than or equal to 1. Okay. Converge. A to power n dn by mod dn dn. And dn takes the value, same value at 0 and pi, 2 pi. So it satisfies 1 by 2 pi. Epsilon equal to 0. This will become square root of dn square. It will, I mean, this should take to mod dn. By this will converge to mod tn, right? Okay. Mod f, this is a mod f epsilon is also less than 1. Okay. Epsilon greater than 0, I define a function f epsilon. Okay. Then I can't. That's what I 1 by 5 dn f epsilon by square root of plus epsilon square. I mean, says okay, d square plus s converge to mod dn. Okay. Dn by the mod dn is can be 0. No, it's not a continuous function. It will converge to mod dn. Yes, that's what. Oh, here you are. I'm sorry. Yeah, I have written it. Exactly. This dn by dn square plus epsilon. I can take dn by mod dn. I can't take it because that's not continuous. So I am using. If I take if I suppose if I can take dn by mod, then I will clearly immediately get it. The supremum will be attained. Here supremum is not attaining. I am producing a sequence, or I mean producing for each epsilon I am producing an f epsilon, which is less than or equal to 1, whose norm is less than or equal to 1, infinity norm is less than or equal to 1, and then this T and f epsilon converge to this mod epsilon converge to that. Okay. If you want, let me repeat. If you compute a norm of something, first you prove always any space norm. Okay. This is what we have proved. We want to prove that norm of this is equal to this number. Okay. First, we prove that this is less. If you want to prove equal to k, use one single equal to k. If that is not possible, you produce a sequence of xi n such that t xi n will converge, norm t xi n will converge to this. Okay. Of course, all three norm xi is less. Here, this norm xi should be less than or equal to 1. Okay. Yeah. So that is what it is. If you these things I have said when we were discussing boundary layer. Yeah. Yes. This is epsilon inside and this. Okay. If this mod f epsilon this will go whatever k equal 0 mod b and t by norm of is equal to this. Okay. Okay. If we have a problem, I will repeat it in the next class. To go through it at home, go through the video. If we have a doubt, we will explain. Actually, I'm also tired, so I'm also getting lost. So let me just finish this and then. Okay. Now, what do you we have proved that so Tn norm of Tn goes to infinity, right? Okay. So what does this mean? Uniform boundedness principle is the following. So yeah, I mean, I'm just restating it. Okay. So if we have I mean, this is each n, you have a Tn. Okay. For each n, you have a, okay. If Tn infinity or of Tn equal to infinity. Okay. Then xi, I mean, this is for a general somewhere x2, whatever. Okay. Here y. Okay. X2. I'm just restating whatever we proved as uniform boundedness principle. Tn is equal to infinity. Of all xi x such that the supremum of T norm Tn set of all xi supremum of norm. If you want, you for simplicity, I'm taking it as C. Okay? So that will be just mod norm Tn xi. This means G delta means intersection of open sets. Oh, sorry, intersection of open set. Intersection of open set. Okay, countable intersection of open set, not intersection. Countable intersection of open set is called G delta. Countable union of closed set is called F sigma. So this is delta set. Okay, it's important is dense set. Okay, so we have what we have. So conclusion, corollary. Tn goes to infinity. Norm Tn goes to infinity. The set C0, 0 to pi, such that Sn F at 0 diverges. This is a is a G delta set. Is G. So for a very big set, this is a metric space. In this metric space, is a dense set F, where this Fourier, whatever the Fourier coefficient, this is supposed to converge as n goes to infinity. This is supposed to converge to F of 0. I mean, by whatever, that's what we expect. But this diverges for a G delta F. Okay, but this is one point. You can get any point like that. Yeah, this one. Okay, uniform boundedness principle. Plus, what I said is less than infinity. Tn is less than norm Tn. The supremum of norm Tn is less than infinity. Use Baer category theorem. This will also follow. Okay? It's the same proof. Okay, just the way. But this is a D delta point because Baer category theorem says that the intersection is not used completely. If you use it completely, you will get this. Okay. Then what? Yeah. Zero. Okay. a function equal to f of t plus a. Okay, just shift it. Where of course you should remember this is with respect to a equal to above 2 pi, it's b. Okay, so then you are using it as a group. Okay, are you then if I hat equal to e power I t f of, let's just compute p hat at t, p hat at n, sorry, equal to uh, is just f of a plus uh, 4. Okay. Now this is equal to, if you use a plus t 0 to 2 pi, it will be again 0 to 2 pi f of t e power minus n plus t equal to s, then t is equal to s minus a. So yeah, that's okay. E power minus a will come. I think e power t. Okay. I plus or minus? I'm a bit confused. Plus, is it? That's plus, correct. It is plus. IAN. Yeah, IAN. So if you use that, yeah, T, Xn T of F. Please verify. Okay, this is supposed to happen. Okay, this is true. So now what I am saying is, so now you got 0. Now you have got a function fa which will diverges at a. Okay, so you get divergence at any point. That's what I'm saying. So given any point a, you have a g delta functions of this c0 2 pi where the Fourier series diverges. Okay, I'm not writing the statement. Okay, the statement is clear. Given any point, there is a g delta subset of, okay, for which the Fourier series diverges. Given any function, the Fourier series is fixed. Okay, whatever using uniform boundedness principle, we proved that there is a g delta for which the Fourier series diverges. This technique you can make it at any age. That's all. Okay. Sorry for taking time at here. Okay. Any doubt?